Okay, thank you very much. First of all, I'd like to thank your invitation to speak in this summer school. Even my presentation is not matching perfectly in the topic of the school. I'm not in the cloud, I'm in the sea. So my presentation is about marine robotics and the applications we are dealing with. We are working especially in the inspection of marine environments. Okay. I'm Gabriel from the Systems Robotics and Vision Group on the University of the Balearic Islands. It's not working. Okay. Well, this is a short outline about my presentation. First of all, I will introduce you basics in marine robotics, why we are interested in robotics, how can we classify the different kinds of robots in the sea, how do they maneuver, how is the sensing, etc. And then I will present some of the projects we have been working in the last years. Okay. In any case, marine robotics is a task of a big team. You will need a lot of machines, a lot of people in different tasks, in mechanics, in electronics, in computer science, in different aspects, and also you will need probably, for sure, infrastructure, not only robots, but also ships to go to the place and deploy and everything, okay? So this is a matter mainly of field robotics. So excuse, but my presentation, as I said, is not exactly in the same field as you have in the school. Okay, why robotics? Why underwater robotics? It is clear that most of the Earth's surface is covered by water, and in the water we have a lot of important things for life, for economy, for knowledge, for science. So we can find a lot of reasons, motivations for working underwater, especially because humans can only dive till around 50 to 100 meters, and it's always dangerous sending manned vehicles to the sea. So what we want to do is send unmanned vehicles to avoid danger to the people. Okay, what kind of vehicles are typical in underwater robotics? It is a raw classification of unmanned marine vehicles. We have on the left the unmanned surface vehicles, which are also used very frequently in marine robotics. And on the right side, we have the unmanned underwater vehicles. What we have in managed surface vehicles are typically these kind of vehicles that you can see in these images. In the first case is a typical catamaran with two propellers, and it can go maneuver autonomously, mainly guided by GPS and other kind of localization devices. And in the bottom, you can see another kind of vehicle for military applications. But if we go to the underwater vehicles, we have only two kinds of vehicles: the remotely operated vehicles and the autonomous underwater vehicles. In remotely operated vehicles, the question is that the robot is connected to a ship on surface through a cable, and all the orders, high-level orders, are given from a human operator through the control station. But this is a very used solution. In fact, is the most around 75 or 80% of the remote of the underwater vehicles are of this kind. But what we try to do is to cut the cable and give to the vehicle enough intelligence to operate autonomously, because we can, in that way, we can avoid the cost of having a ship on the surface with all the staff, which is really expensive. And also we open the maneuverability and the area that can be covered without the cable. Okay, we free the vehicle to move. Okay, but in the case of the ROVs, there are, let's say, two kinds. The first one is the free swimming, which are, for example, this little example, which is only a camera with a cable and two propellers. But there are different and higher, bigger vehicles with high capacity, and even bigger with much more energy and capacity of interacting with the sea bottom and recovering samples, etc. Also, in the remotely operated vehicles, we have another class, which is bottom crawling vehicles. And these kinds of vehicles are mostly used in underwater mining. But what we are interested in are the AUVs, okay? In AUVs, which are vehicles without cables, we can distinguish mostly surveying vehicles and gliders, and certain third class, which are the intervention vehicles. Okay, gliders are vehicles that are designed to be used in long-term missions. They can stay in the water for weeks or months. So they need to use a mechanism of movement very simple and with very low cost of energy. How do they do that? They simply use a little bulb that can be inflated or deflated, and with this little change of weight, the vehicle will be positive or negative buoyancy, will have positive or negative buoyancy. So it will go to the bottom, and when it reaches the seabed, it will go up. So it don't has any clear control about the path while it's under the water, and it only can send its location when it's outside. Okay, but with this kind of vehicles, as I said, you can have a mission of around weeks, and even in some cases, there are some experiences that with this kind of vehicles, they have crossed all the Atlantic Sea from the States to Portugal. Okay. The most typical kind of vehicles are survey vehicles, and these are, in general, torpedo-shaped vehicles that use some kind of propellers and bladers to navigate. Here you have some examples from different companies, and the white and yellow one in the corner, I will present you later with more detail because it's the one we are using. Okay. And finally, there are another kind of vehicles that have also the option to use an arm and manipulate. Okay. These vehicles can only take images, data, temperature, salinity, or other kind of sensing, but cannot interact. But in that case, this is one of the only vehicles that also can use an arm to make some interaction interaction with the media. Okay, there are also some hybrid solutions that are in between the remotely operated vehicles and the autonomous underwater vehicles all around the world. And also, for sure, a lot of bionic morphologies that are also in development and trying to use some advantages of biology. Okay, in the classical kind of vehicles that like the one we are using, the maneuvering is can be achieved in the immersion and immersion essentially by changing the buoyancy of the vehicle. This can be done with a static mechanism that simply filling or throwing out the water of the tanks or with the ballast releasing. But in general, we in robotics, it is more usual to use the dynamic solutions, which consist on using vertical thrusters that will push the vehicle to the bottom and then stopping or reversing the speed of the direction of the thruster going up to the surface. Okay, and in the case of the heating, it can be achieved with a rudder, like the ship. That would be this solution. But in general, it must use the differential thrusting. So this is the simplest solution, and the one we are using in this vehicle here, the Turbot, which is, as you can see, it has two propellers in the rear, with so it can turn with the differential mechanism and with the vertical thruster in the center that will be used to emerge and release the vehicle. Okay. Okay. Going to the sensors. In the sensors, I will not pass through all this long list, just to remember something about the different kinds of sensors we use. According to the functionality, we could distinguish between the sensors that are used for the navigation, that means knowing where the vehicle is and where it has to go. And also we have some monitoring sensors used to ensure the integrity of the vehicle. And then we have a large list of mission sensors depending on what we want to do in the sea. We used to use, the most used in our case is using optical imaging systems like cameras, but there are many, many different kinds of sensors that can be used depending on the objectives of the mission. Okay. This is the typical acoustical system for positioning. The problem underwater, one of the biggest problems in underwater is knowing where the vehicle is. It is a very different problem to the terrestrial robots, because if you have GPS, you have a very good location positioning system. And if you are indoors, you can install different beacons to locate your vehicle, or you can have a map, a precise map, and you can locate. But underwater, we have a very big problem of position. So we tried, there are different solutions, and most of them are based on acoustics. Here you have typical solutions. The long baseline, which is this one, consists on installing some transponders on the sea bottom that are hearing the signal from the ship and then answering with an echo. So with the difference of flying time from each answer, we can know where the ship is. But starting with this idea, there are different variations. The most usual one in robotics is this one, where we only use one transponder, but this transponder has different, excuse me, this hydrophone here has not only one, but 3 or 4 hydrophones placed at a different distance. So this system is able to detect the distance and the bearing of the position of this transponder. So we place this kind of transponder on the vehicle, and we use to know where it is on the surface. There are other sensors that can also be used and are frequently used to know where the vehicle is or how is it moving, but all of them are incremental. All of them give us relative movement, not absolute movement. The only one that give us absolute position is this kind of sensors, or of course the GPS when the vehicle is on surface. When we are underwater, we need to use other sensors. One of the typical one that our vehicles use is what we call a DVL, a Doppler velocity log, which is based on the Doppler effect. I'm sure all you know that the Doppler effect is the physical effect that gives us shortens the wavelength when we have a source approaching receptor, and increases the wavelength when this source is going away from the receptor. So based on this effect, there are these devices called the DVL that send an acoustic signal to the bottom and wait for the echo going back. With this frequency shift in all the beams, the system can calculate how it's moving on the plane. Okay, this also is used on vehicles underwater. But as you can see, the accuracy in the best case is not as precise as it would be. It would be desired, and in some cases the ranges doesn't allow us to go very high from the sea bottom. Okay, there are for sure other options like gyro compass, like in terrestrial robotics, but it's also an incremental system. I'm not going to discuss about how it works on an inertial unit. I suppose that all you more or less know. And for sure, when we are outside of the water, we can use the GPS. To sum up all this, excuse me, I wanted to go to this. To sum up all the sensing information that we need to locate a vehicle underwater, in this slide, you can see that we can receive from many different sensors absolute positioning and a relative position that will be integrated with different kinds of sensors to finally the navigation status, which means the 6 degrees of freedom pose of the vehicle in water. Okay, but this is from the theoretical point of view, it's clear what we have to do, but in the practical side, there are many problems because the absolute positioning is a low frequency and very noisy, and we are very affected by the drifting of the vehicle when we are only using the allometric solutions. Okay, suppose that we know where the vehicle is. Now we are collecting data in our mission, and we want to communicate to the outside what's happening there. So this is another big problem in underwater robotics: how to communicate. We can communicate data using acoustics, and in some cases we can also use optics, but I will briefly describe the problem. Underwater, the speed of sound is around 1,500 meters per second. So this is not the speed of light, of course. And moreover, this depends on different parameters of the water. That means that when I send an acoustic signal from an emitter to a receptor, the speed can change in the past. It will change because of salinity, because of pressure, because of temperature of the water. So there is imprecisions about the distance that the signal has covered. And also we have the problem of the attenuation that also depends on different kind of parameters. That means that we will have a serious problem of communication, and this is one of the reasons that stops the possibility of doing underwater robotics in the cloud, because to be in the cloud you need a good communication, and in the sea we don't have good communications. Okay. We also can use optics, and in the last years there are some solutions using optics, but the most high-end, the high-end optics modem nowadays, it's around 10 megabits, not more, and the range they can be used is very short. So we cannot deploy robots in a big area. We can have communication with them. Okay, I don't know, I don't have much time to discuss about the problems in optics, but I will go. Okay, this is the applications. What kind of applications are the most typical in underwater robotics? This is a short list of, and we'll go through a short revision. For example, in natural resources, we have the possibility of using underwater robots in fisheries and fish farms. You know that in the next years, nearly half of all the seafood will come from the aquaculture. So there are a lot of business in this kind of infrastructure, and nowadays they are using, for example, robots to inspect the integrity of the nets and detect where there are some holes that the fish can go away, etc. And also they can be used, and they are used, the robots, to navigate through the installations and detect the concentration of different kind of elements that can be dangerous for the fishes and all the species that are in the farm. Maybe this is the most known application of robotics in underwater. We have a lot of mining in the sea, and especially for oil drilling platforms, and also now in the deep sea mining systems. And there are a huge industry trying to use these vehicles to solve problems and to dig and recover mineral resources. And of course, now that the renewable energies like windmills and tidal systems are in development, the vehicles, the underwater vehicles, will be used for the maintenance tasks. This is another example of application of underwater robotics, and probably most of you can remember the Deepwater Horizon platform in Mexico that crashed in 2010. To give you an idea of the complexity of this kind of infrastructure, Horizon was drilling at 1,500 meters depth, but the oil layer is more than 5,000 meters down. Okay, so when the accident happened, a lot of systems were sent trying to solve and to stop the oil going out of the well, and some of them were robots. Okay, they sent the gliders, ROVs, and also this AUV from Woods Hole in Rhode Island was one of the vehicles used there and one of the responsible for detecting where the oil was going out and trying to stop it. Okay. Going to science, these are some, this is a big picture of one of our infrastructures here in the Balearic Island. This is the coastal observing and forecasting system. This is used for detecting how the shore, the coast and the beaches are evolving depending on the weather and depending on the construction of docks and studying the currents. And in this system, in these observation systems, we use different kind of systems like permanent platforms like this, which is installed in the bottom and cabled to the central station. There are different kind of robots and also different kind of moored buoys and resting buoys, and also gliders. Okay. This is another typical installation, not here. This is a deep sea ocean network in Canada, in front of the Eiffel, in front of Victoria, and also by Vancouver. Okay, and this is a very huge network of sensing stations, especially centered in geology. But in that case, I want you to see this slide because we will compare this one with the one we are developing at this moment. This is a cabled deep sea network with huge stations and using big robots for their maintenance. We will see the difference with the one we are developing okay. This is another typical application in archaeology, and I will not extend my exposition, but it is clear that using divers, the depth that can be operated is very limited, and nowadays there is an important action for using vehicles, underwater vehicles, unmanned vehicles for recovering all this cultural heritage. Okay. Humanitarian is also a very well-known application of underwater robotics. And we took this example of the Air France crash in 2009 in the middle of the Atlantic, flying from Brazil to Paris, to inspire one of our research projects. In that case, the plane crashed, sent his last position here, and the experts estimated that the area where they should try to find the remains would be around 7,000 square kilometers. They used, apart from many other resources, they used 3 units of this vehicle, the Remos 6000. And with this vehicle, they used the acoustic systems, imaging systems, and detected some shadows in the bottom on April 2011, almost around one and a year later. And then they sent this vehicle, and after 2 weeks, they found the remains of the vehicle, and they were able to recover the black box to determine some of the causes of the accident. Okay, in that case, we reproduced this situation with an autonomous vehicle, as I will show you later. Well, of course, defense is also an application, and for sure, you can imagine anything, and I'm sure it's already done for defense. Okay. This is a study about the market, just to give you an idea about what's the amount of money moving in this field of robotics. And as you can see, in 2020, it's projected to reach around 7,000 million and growing up to at a 40% per year. Okay, and here you can see that of all the underwater robotics market, around the 25% is AUVs and 75% is ROVs. These are also many applications that can be where I use the robots, and if in this column in green you can see where the ROVs are used, and in this where the AUVs are used. So you can see that almost most of the AUVs are used in geology, biology, environmental monitoring, archaeology, aquaculture, mine countermeasures, etc. Okay, after this introduction to what can be done with robotics, I will go to what are we doing in robotics. Our group is called Systems, Robotics, and Vision, and we are around 10 members in the staff, and also we have changing around 10, 20, sometimes a little bit more PhD students. We have an activity of 25 years, and you can read about our activity in our website. You will find all the updated news about what we are doing. Okay. Our vehicles, we use an underwater vehicle and a surface vehicle. The underwater vehicle is a unit of Sparrows, which is a commercial system, but we have changed all the front of the vehicle, putting our sensors for specific missions that we try to solve. The main systems we have placed is the location system, some focus, and the cameras, because we try to use image for all our applications. Okay, this is a light vehicle. It's around 20 kilos and can be operated with 2 people. And we can operate, depending on the energy we are using, around 8 to 12 hours. Okay. This is the structure of the computers and of the sensors. Well, I only want you to know that you notice that we use a computer only for testing the sensors, the navigation sensors, and we use another computer for the cameras, because the image processing is very huge and cannot be made by the same computer. This is a surface vehicle. It's a very low-cost vehicle that has been done with 2 pipes and an electronics box, and we use it. We have put in the vehicle the USBL and the GPS and the Wi-Fi. Okay, the question is that, as I said before, when you have the vehicle in the water, you only will have absolute positioning from the GPS to the USBL from time to time. You only have a exact positioning around 1 Earth, or even lower, because that depends on the distance from the meter. If the vehicle is around 1 kilometer away from the ship, you will have the signal going and going back. That's 2 kilometers. That's around 1.5 seconds. What happens during this time? During this 1.5 seconds, the vehicle has to go by odometry, and it will drift because the measuring system, the sensing systems are not very precise. So you will have to use high rate sensors in generating the relative position and low rate sensors to correct and have the absolute position. Okay, we started working in the first configuration, the up configuration, using the USBL attached to a moored buoy and working on the waterfront, on a dock, and sending the vehicle. But this has a lot of problems because the cable is not very long, so the emitter is very close to the sea bottom and to the walls of the dock, and we have a lot of external perturbation because close to the beach and to the dock we have all boats and people swimming, etc. So then we, in some cases, we started using a support vessel, but that means that we need to pay a lot for support and the crew, and or maybe in some cases ask a friend, if you have it, to borrow the ship. So the third solution was using our own autonomous vehicle, and that's the reason why we started working in this configuration, which is the one we try to use the more whenever we can. Okay. Okay, going to the projects. I think I don't have time to explain all the projects we have been doing in the last 20 years. This is only a short list. Let me tell you that all these projects were happened from 2010 to 2018. All of them are about search and rescue or industrial applications like pipe transportation, pipe connection, or in that case, Naples project is about archaeology, detection, mapping, etc. The one here, Trident, is a recreation of the accident of the plane that we did a few years ago. This is an European project with the participation of universities from Italy, from Scotland, Spain, and France. This was a simulation of an accident. We throw the marking black box in the sea in an area, and we sent a robot to inspect the area. This is a recreation. the images were used to generate a mosaic, and on the mosaic, an operator determined where the black box was. So the vehicle was able to recover the position of the black box and grasp it. Okay. This is the detection of the black box seen from the camera on the vehicle. This is the vehicle grasping the black box. All the operations are fully autonomous. There is no cable. There's only well, there are cables, but they were only used to record the images to report the success of the project. And for sure, we were not working at 2,000 meter depth. It was only around 25 meters. Okay. You can see a lot of people happy with the success of the project. Oh, okay, and the other projects are, for example, in Triton project, we manipulated some connectors and cables in a permanent station. And in the twin boat, as I said, we use two vehicles to cooperatively transport huge objects. And in this project, which is also a European project, is a civil protection project that pretends to help in detecting the oil spill when there happens an accident and you have an oil spill in the sea. Use different kind of vehicles, aerial and underwater, to detect where is the oil, and with the simulator try to predict where the oil will go to help the civil protection to stop the oil reaching the coast. Okay. But in the last years, we have centered our activity in observing the marine environment. Why? The reason is very clear. We are in an island. We are in a very fragile environment, and we have a lot of people working in biology and in oceanography. All these institutions are research institutions in the Balearic Islands, the Instituto Mediterráneo de Estudios Avanzados, as I said before, the Coastal Observing and Forecasting System, the Oceanographic Center, the Spanish Oceanographic Center also has a center here in the Balearic Islands. And also our university has a marine biology department. So we started to speak with them and present our capacity, and they presented us their problems. Okay, so I think it's reasonable to work with them because they are more than 150 researchers and technicians in the biology, and there are a lot of problems, and so we can take advantage of all the infrastructures they have. Okay, so what kind of research opportunities we have when we go to the marine environment? There are a lot of problems. Unfortunately, there are a lot of problems. We have problems of pollution, with oil, with plastics, any kind of marine litter. We have problems with species that are in danger, like all these that you have here, the nobilis, the hippocampus, etc. We have also the presence of alien species that come in the tanks of the big ships, and when they throw the water away in the sea, they spread this kind of species, especially coming from the tropical waters. For example, we have the Alimeda and the Tabulerpa, okay? And well, different kind of impacts from the anthropogenic origin. These are just a short list of projects we are working in. For example, in the case of the pollution, as I said before, we have been working in a project about oil spill. In the case of the threatened species, especially the Posidonia, we are still working in the Detect Post project that I will speak about a little bit. The grass map, which is also a project with the University of Southampton, that we have been using different kinds of robots to map the presence of the Posidonia oceanica. In the case of the alien and nuisance organism, we have also in development the project about the detection of the algae, the Alimeda encrasata, and in the case of the anthropogenic impact, we have been involved in a project about the problem of the fishing nets, etc. And the final project, the PLOM, which is the one we are now what's involved, is the one about the ecological indicators. I'll speak you about a little bit. Okay. The Posidonia oceanica is one of the leitmotif of many projects because it's a very important, it's not an seed, it's a plant in the sea that has a lot of threats. The bilge cleaning, the anchoring, the dredging, the troll fishing, the raw sewage. All these threats put in danger the Posidonia, and the Posidonia is very important for life in the sea and for the quality of the water, because with Posidonia oceanica, the waterfront is protected when the bad weather and the waves throw to the coast. Many fishes live in the Posidonia oceanica, and it has a strong impact in the CO2 trapping. So the traditional way of inspecting the quality and the presence of any kind of plant or life being in the sea is with scuba divers, but this is quite time-consuming, limited in life and death, and it's not an accurate method, and also it's dangerous for the people who are doing that. So we started using robots to reduce the mission time, for sure cut down the human risk, and also cover larger areas and deeper areas. More advantages of using these robots is that all the experiments can be repeated from time to time. Okay. And you can have time series, which in biology is very important. You can detect if the plants are growing or are decreasing in a precise way. Okay, I think that I don't have enough time to present all the project, but these are different images of the vehicle surveying areas, different views of Posidonia, and what we used to do in that case is, first of all, building mosaics of the area covered, which is a very important, which it provides very good information to the biologists to observe at larger areas and detect how is everything going in the seabed. Okay. Well, what's happening now? Well, this is another project about also about Posidonia, where we studied the effect of sewage pipes in PALMA Bay. There is a pipe here, and we expecting an area very close to the pipe and a contrast area, a reference area, 8 kilometers away. And we found, and we demonstrated that the sea bottom close to the pipe is very damaged. The Posidonia is dead or almost very sick. And instead, when you go to a reference area, you have a very healthy Posidonia. Okay, well, these are other kind of projects that we are involved in the detection of alien organisms or in the real-time monitoring of different kinds of species. Okay, 2 minutes for PLOM, sorry. PLOM is one of the biggest projects we are now involved. It is the idea of PLOM is the use of long-lasting observation in marine ecosystems with low-cost platforms. I'm going to the main idea. We are developing this kind of platforms which are easy to transport, to deploy, and to recover. They are not cable. And we will use few of these platforms to permanently record data of the area surrounding them with cameras and with other sensors. But at the same time, there will be vehicles covering the area in between. This information is complementary in the case of the remote of the landers of the fixed stations. They will record and they can record fishes, for example, because they don't scare. But in the case of the AUVs, for the noise produces that the fish go away, but we can detect presence of evidence of life. I will show you just a little bit. So the vehicle will be for almost 1 week working the area, and when the batteries run out, we will have the ability to go to a docking station, recover energy, transferring data to these pop-up boards that will be sent up to the surface. So this is the only way to have high volumes of data when you are underwater without cables. Otherwise, you only have the acoustic communications that's only 5 to 10 kilobytes per second. That's you cannot send video, of course. Okay, the objectives are here, but we are centered in the eye, the UID, developing techniques for processing and analyzing images, and okay. As I said before, we plan to use systems to detect the evidence of life. When we detect the evidence of life, we plan to stop the vehicle and go closer or stop and analyze better these evidences, trying to detect this the life. In our case, the target is the no-ray lobster. And the case of the landers is to record images and recognize the species and size them. Okay, this will be deployed in the next years in different spots, in shallow waters, in deep marine, in deep waters, and also in a long term duration. Okay. Sorry for my delay. These are the first experiments with the lander that has been deployed for 1 month in the coast of Barcelona, and now we are okay. Sorry for my delay. Just a few images about different projects we have been participating, and the advantage of working in underwater robotics is that you will work a lot with many people. You will have hard times, but you also will have funny times. Okay, thank you very much.
So that's what we hope. I'm investing in that. As I said, I also have a lot of vision of this. I mean, I'm also it's really hard actually. So I want to know how do you tackle this how are you able to get all this vision of because
Up to now, we only have been working with clients. They don't move a lot. We work with Alibaba, we work with Posidonia. Okay, and from time to time we can see some fish, but it's not the target. And in the project. In the PLOM project, what we plan to do is that the static platforms, the landers, they can record fishes because they don't do any noise. They only flash every 30 seconds. They take an image. And we have some experiences, we have had some experiences now in this August that the fishes are not scared and they can be, we can take pictures of fishes. But in the case of the AUV, of course, the propellers make some noise and it's very difficult to detect. And, well, the images of the fishes that you can take are not significant. In that case, we will record or detect images or static life being. For example, a starfish, the burrows, and some other, for example, remains of dead animals. And this, we have been told by the biologists that they can treat this data and infer some important information about the quality and the health of the seawater. But of course, it's very difficult going with a camera and recording fishes.
Very better, yeah. So I have a couple of questions on the global project. You mentioned that the base is moving towards the central station. How is that happening? Or the deployment of the voice?
The AUV is planned to go and move in the surroundings. And when it run out of battery, it will go to the central unit and will dock and we'll charge again the battery and transmit the data. Yeah.
But then the central station is permanently connected to energy source.
No,
okay.
It will also be with batteries.
Okay.
Yeah, but a huge packet of batteries.
And then the second question was more on the type of data. So as far as I understood, all of the computation is done on board on the devices. Do you have any foreseeable usage of cloud computations for analyzing the data that you're collecting underwater?
Well, underwater there will be some image processing, basic image processing, especially in the vehicle. In the case of the vehicle, what we want to do is that we don't. Let me check. We don't want to make a regular inspection. The typical way of working with a vehicle underwater is a long moving surveying. But as you can see in the first column, the inspection is also it's linear. It's a mission planning and it's an execution and the final. And the vehicle in general doesn't have any kind of, well, it doesn't use any information during the mission. But we are now, we have just finished PhD thesis in which we have been able to process online and to determine how the mission has to be changed to recover the more information during the mission. So we plan to use this strategy, and when the vehicle is recording the sea bottom and you can detect some kind of evidence that is interesting for you, for example, you can stop the vehicle and go a little bit down and try to give better information.
Thank you.
Thank you very much. Thank you very much.